perceiving color. So, we humans are visually oriented and we have very good color vision. Um, why do we have color vision? Why did we evolve it? Well, color signals help us to classify and identify different objects. We actually use color to help us classify things. Color helps us to organize objects, to identify what's part of what and what isn't part of what, and to build our internal representations of those objects based on color. And then finally, color probably helps us to find food. Probably is an evolutionary advantage to hunting for food. So that's probably the one of the primary reasons why we evolved the ability to perceive color. For example, if you look at this picture, which is from your textbook on page 200, figure 9.1, you'll notice that the berries on the bush are a lot easier to identify than when you can see in color versus when you can only see black and white. And in fact, birds, the types of birds that would eat these berries, can perceive colors and are actually evolved to look for certain types of berries of certain types of colors. And we have this co-evolutionary strategy where plants have evolved colors to display their fruits that they want other animals to eat so that their seeds can be spread out. We use colors to identify foods. So this is a classic experiment from about 15 years ago by Tanaka and his co-workers where they had people identify common fruits and vegetables. On the left you can see fruits and vegetables such as carrots, lettuce, and bananas, and then on the right you see the exact same vegetables but they're colored weird. And it turns out that when you show the miscolored fruits and veggies, it takes people a longer time to name them. There's more cognitive processing involved because you're missing that critical color cue that tells you what it is, because the modern fruits and vegetables that we have nowadays have certain colors. The ones that we see in stores nowadays have certain colors. So what do we perceive? Well, as humans, we perceive a certain part of the visual spectrum. The fundamental colors, the basic colors, are red, yellow, green, and blue. And there's a color circle here that you've probably seen before that represents all of the main colors that we can perceive, going all the way from red, orange, yellow, blue, green, and then blue, and then indigo, and then finally violet, all the way over to red again. That's the color circle. The perception of these colors can be changed by the intensity, which makes some colors look very bright, and then some colors look very dull, like with a pastel color, for example. And then colors can be also saturated. So if you add white to a color, it'll be less saturated than a full-blown color. Again, making those sorts of types of pastels that we're used to seeing. This right here is a representation of the visual wavelength. That part of the spectrum, the electromagnetic spectrum that we can perceive. Now, the part that we can perceive with our eyes goes from 400 nanometers all the way to 700 nanometers. And this represents, for us, our eyes, it represents the colors going from red from blue going all the way over to red. So the longer wavelengths, the 400 nanometer wavelengths on the left-hand side, we perceive as blue. And then the shorter wavelengths we perceive as green, even shorter yellow, even shorter red. And of course we have all the colors in between, like orange, for example, is between yellow and red. But depending on the wavelength, depending on the distance, the nanometers of, the number of waves per nanometer of energy that is hitting our eyes, we're going to perceive different colors. And again, as you can see here, the longer wavelengths, which are 400, are going to be perceived as more bluish, and the shorter wavelengths, 700s, are going to be perceived more as reddish. So here's a more detailed breakdown of the different types of colors based on the wavelengths and the colors that we perceive those wavelengths. So any electromagnetic energy that's traveling at 400 to 450 nanometers looks violet to us. Violet. 450 to 490 nanometers looks blue. 500 to 575 nanometers appears green. 575 to 590 nanometers looks yellow. 590 to 620 nanometers looks orange. And then finally, the shortest wavelength, 620 to 700 nanometers, looks red. Now remember, we're talking, these numbers represent frequency. In other words, the number of waves, complete waves, that appears, the numbers represent the distance between waves, one wave and the next wave, right? So if we say 620 nanometers, that means there's 620 nanometers of distance between the start of one wave and the start of the wave next to it. So the shorter waves have the shorter waves, which are smaller, they're more compact, are going to have higher numbers than the longer waves, which have lower numbers. The color that we perceive of an object is determined by what light gets reflected off of that object. So if you're looking at an object and it looks green to you, that means that the only light that's bouncing off that object and hitting your eye, in other words, the light that's being reflected off that object, the only light that's coming off that object and hitting your eye is traveling at about 500, between 500 and 575 nanometers, which is green, of course. If you're looking at an object and it looks blue, that means that the light that's bouncing off that object is traveling between 450 and 490 nanometers. So the only way we perceive color is off of the wavelengths, the light energy that's bouncing off of something, that's being reflected off of something. We have a way of quantifying how much is reflected is by computing or by measuring what we refer to as reflectance curves. And basically what we do is we plot how much light is bouncing off of something as a function of wavelength. So, we look, for example, for the blue wavelength, and we see that X percentage of light bouncing off an object is in the blue spectrum, and then X percentage of light bouncing off that object is in the red spectrum, etc., etc. Chromatic colors, or what we refer to as hues, are objects that preferentially reflect some wavelengths. So, which is pretty much, if, most objects, in our usual everyday experience, almost every object in our usual experience has hues associated with it, so colors associated with it. And it's going to reflect only those colors that don't get absorbed by that object, and whatever doesn't get absorbed is going to bounce off of there and reflect off of there into your eyeball. And this is referred to, this process where only certain wavelengths bounce off and go into your eye, is called selective reflectance. So for example, if you're looking at a green object, right, and you shine a white light on it, white light has all the wavelengths in it, everything. If you shine a white light at an object that's green, well, what's going to happen is all of the other colors are going to be absorbed by that object except for the green one. The green wavelength will not be absorbed, so it'll bounce, It'll bounce off of the object. All the other ones will be absorbed by the object, but the green one will bounce off the object and end up hitting the retina in the back of your eye and activating the cones for green. And you will end up perceiving that object as green, and that is selectively reflecting the color green. There are also colors that we perceive as achromatic. There's no hues. In other words, there's no colors. And these are white, black, and gray, which of course are important colors, right, for art and for fashion and whatnot. So on this slide, which is from your book on page 202, we have some very simple examples here of the two ways that color gets to your eye. That is selective reflection and selective transmission. In both examples, in A and B, there is white light being shined on a surface. Now, white light contains all the wavelengths, or at least usually contains many of the wavelengths, right? In this example, it contains blue, green, yellow, and red. In selective reflection, what happens is the white light shines on an object, and colors get absorbed. Certain colors get absorbed in the spectrum. Certain colors out of that light get absorbed, and certain ones don't. The ones that don't get absorbed bounce off of the object and end up entering into your eye. And whatever bounced off the object that didn't get absorbed, whatever bounced off the object ends up going into your eye, and that's what you perceive the color as. So in the example in A, we see that blue, green, and yellow got absorbed, but red did not get absorbed. It bounced off the object and got reflected off, and ultimately some of it ended up in your eye, which you then perceived as red, because it is in the red wavelength. That is, it's one of the shorter wavelengths of light. In the other example, we have selective transmission. So we have a filtering type effect going on here, where again we have white light passing through an object that filters out certain wavelengths. So for example, we have in this example again, we have an object that filters out blue light, green light, and yellow light. Those wavelengths are absorbed by this object, and the only one that isn't absorbed is the red one. The red one is allowed to pass through and go into the eye, and once again, whatever doesn't get absorbed and that passes through and ends up in the eye is the color that you're going to perceive. In this example, the red, green, and yellow got absorbed by the object, but the red did not get absorbed. It passed through, and ultimately what you perceived passing through was red. Here's an example of some of these, what your book referred to as reflectance curves. This is an example here of reflectance curves for different objects and different pigments, right? So if you look at the top, there's a line that just goes almost straight across, and that's the line for white paper. That's a line that represents what is being reflected off of white paper. Now, white means that pretty much all the colors are represented in the spectrum. So as you can see, it's pretty much a flat line because it's reflecting blue, green, yellow, red, everything. It's just a flat line. Obviously, if you look at the dashed line for the blue pigment, you'll see that it's highest in the blue part of the spectrum, and then it goes down. The line for the green pigment goes highest in green, of course, and goes down. The line for the yellow pigment goes highest here, and there's a little bit left in red, and then it goes down. A tomato, which of course we perceive as red because everything's absorbed except for the red light. So we see that as red because all the light that's hitting it in the blue and green and yellow is being absorbed, but the red bounces off. A gray card is perceived as having very low amount of color, of course, and there's no hues, it's just flat across. And of course, black paper is black. The reason we perceive it as black is because it doesn't reflect anything. The light hits it, but very little light bounces off of it. So as you can see, the reflective curve for black paper is all zeros across the entire spectrum because there's nothing being reflected off of it. Compare and contrast the black paper with the white paper, right? The black paper, we have nothing reflected. the white paper where we have everything reflected, and then we have the pigments and the objects somewhere in the middle. So if only short wavelengths are reflected or transmitted off an object, we're going to see blue. If medium wavelengths are reflected off an object, we're going to see green. If there's a mix of long and medium wavelengths, we're going to see yellow. If there's just long wavelengths, it's going to look very red. And if there's a mix of all three, long, medium, and short wavelengths, we're going to see white. Make sure you commit this chart to memory. It's going to be very helpful to you to understand the relationship between the physics of the light, the wavelengths of the light, and the psychology of what it is that we perceive.